this lecture, we're going to define a bunch of terms that will be used later on in the course. So first of all, we're going to start off by talking about the dimensions and systems of units that we're going to use. And we're going to be using two in the course. The first one, of course, is SI units. So in SI units, the unit of mass is kilogram, the unit of length is a meter, unit of time is a second, and the fundamental unit of temperature are degrees Kelvin. We're going to be talking a lot about temperature scales later on. So those are all basic units, but there are also two derived units that are important in this class. So a unit of force is a Newton, and that's defined as a kilogram meter per second squared. And the unit of energy, very important, is joules, and that's defined as a Newton meter. So we'll be talking lots about this later on. Here we're just setting out what the SI unit of energy is. And the basic SI unit is a joule. Now in practice we will use kilojoules much more often, and that of course is just 1,000 joules. The other system of units that we'll be using are English engineering units. In English engineering units, a unit of mass is a pound, a unit of length is a foot, a unit of time is a second, and the basic temperature scale is degrees Rankine. So this plays the same role as degrees Kelvin in the SI units. And again, we're going to be talking lots about temperature scales later on. So again, those are all fundamental units for the same four quantities as we talked about in SI, but there are two derived units that are important. So the unit of force in English engineering units is the pound force. So this gets a little bit confusing because the same name is used for force and mass, but these are two different things. And the subscript F is put on the pound force in order to help us distinguish between these. So the unit of force in English engineering units, a pound force, is defined as 32.2 pounds mass, feet per second squared. So notice that is a pound mass, this one up here. Sometimes you'll see a pound mass written like this with a subscript M on it to, again, help us remember that that's a pound mass, but in this class just a straight LB with no subscript refers to a mass, and if it has a subscript F on it, it refers to a force. The unit of energy in English engineering units is a foot-pound, and remember that that's a pound force there because it's a force acting through a distance, pound force times feet. Now there is another unit of energy that we'll be using quite a bit, and that's a BTU, but that's just there's a conversion between those two. The basic unit of energy in English engineering units is the foot-pound. So those are the two systems of units that we'll be using, and we'll see as we do examples throughout the course how these both work. Now we want to define a bunch of terms that we're going to be using in the class. So I call this a thermodynamic glossary. So these don't necessarily have a connection with each other, so this is a little bit disorganized as we go forward here, but there's lots of terms that we need to define. So we want to start off by defining a thermodynamic system. Now later on in the course we'll see that we're going to be talking about conservation laws, conservation of energy primarily. Well, we need to clearly define at the beginning of an analysis or the beginning of a problem what we're doing conservation of energy on, and that is called the thermodynamic system. So a thermodynamic system is a portion of mass or space which we want to study. So we're going to be drawing boundaries around that mass or space as part of our solution technique later on, and that'll be called a system boundary. Now in addition to the thermodynamic system, there is something called the surroundings, and the surroundings are simply everything in the universe except the system. So everything is either in the system or it is outside of the system. So the system and the surroundings make up everything. So system plus surroundings is the universe. So we'll be using those terms, system and surroundings, a lot. We'll be talking about energy transport between the system and the surroundings, maybe mass transfer between the system and its surroundings, and that's what we're referring to. Now the system boundary, also known as the control surface, is the surface that separates the system from its surroundings. So we'll be talking a lot about heat and work transfers across the system boundary, and eventually when we look at open systems, there'll be mass transfer across the boundary as well. So there are two types of systems that we're going to look at. There are closed systems, also known as a control mass, and open systems, also known as a control volume. A closed system, the single thing that you need to remember that defines a closed system or determines whether you're talking about a closed system is that there is no mass flow across the system boundary for a closed system. There can be heat transfer, there can be work transfer, but there cannot be mass flow across a closed system boundary. So a typical example of this, and the little illustration that we'll see many times when we're looking at closed systems, is a small piston cylinder device with a substance of some kind in it. We can do work on that substance, perhaps by compressing it. We can have heat transfer with the surroundings by lighting a blowtorch up and heating up that system, but the mass is contained. So we have a system boundary, there's work transfer across the boundary, heat transfer across the boundary, but whatever this substance is not transferring across the system boundary. So that's not happening. An open system, on the other hand, mass does flow across the system boundary. So again, that's the single feature that distinguishes open and closed systems from each other, is whether or not there's mass transfer across the boundary. So here's an example of an open system, and this is a compressor. So we'll define a system boundary that is around this device, and we're interested in energy transfers across that boundary, but we also have mass flow in to this control volume there and mass flow out of the control volume there. So this is an open system analysis. This system also has a work transfer across the boundary. Next thing we want to talk about is thermodynamic state. So the thermodynamic state is the condition of a system as described by its thermodynamic properties. So clearly we need to look at some thermodynamic properties here to see what thermodynamic state means. So thermodynamic properties, here's a list of most of the thermodynamic properties that we're going to be talking about in this course. So we'll go through this list. So we have the name of the property here. We have the symbol that we're going to be using for the property there. We have its units in SI here, and we have its units in English Engineering System here. So we'll take a look at each of these. Now the thermodynamic state is just the list of these properties that define the current state of the thermodynamic system. So the first one is mass. And the symbol we'll be using for that is M, lowercase m, and in SI units that's kilograms, and in English Engineering units it's pounds. So that's just one of our basic dimensions in both of these systems of units. The next property we're going to look at is the volume of the system, and for that we use an uppercase V, and in SI units that'll be meters cubed, and in English Engineering units cubic feet or feet cubed. Next is energy, and for that we'll be using an uppercase E, and the typical unit in SI is kilojoules, could be joules, but usually it's kilojoules, and in English Engineering units that's foot-pounds. Next is internal energy. Now the distinction between energy and internal energy we'll be getting into in a little while. I'm not going to do that right now. This is just a list of units. This symbol we're going to use for internal energy is an uppercase U, and again it's a form of energy, so it's kilojoules or foot-pounds. Next is enthalpy. So that is a new term for you. It is a form of energy. We'll be doing a detailed discussion of exactly what enthalpy means later on. But its symbol we're defining right now is an uppercase H, and because it's a form of energy, it has the same units as energy and internal energy, so kilojoules and foot-pounds. The last thermodynamic property we're going to talk about here is entropy. This is an important property connected to the second law of thermodynamics that we're going to be talking about a lot later in the course. The symbol we use for entropy is an uppercase S, and its units are actually kilojoules per degree Kelvin in SI and foot-pounds per degree Rankine in English engineering units. So we're not going to define entropy right now, we're just laying out what symbol we're going to use for it. So this set of numbers that go along with this set of properties defines the thermodynamic state of the system. Now, the fact that all of these units here, or all of these symbols that we're using here, are uppercase is significant, and I want to talk about that next. So if we look at another list of thermodynamic properties here, just continuing on, the first two of these are temperature and pressure. So these are new, they weren't on the previous slide. So the symbol we'll be using for temperature is an uppercase T, and of course the units are Kelvin or degree Rankine. The units for pressure, uppercase P, units in SI are pascals. Now a pascal is a Newton per meter squared. Now a pascal is a Newton per meter squared, and the units of pressure in English engineering units is pound force per foot squared, so force per unit area, the same as in SI. So those are two new properties, new meaning they weren't on the previous slide. Now the next 5 properties, if you look at the previous slide, you may notice that these 5 properties were also on the previous slide. So we'll just go back. So we're talking now about these 5 properties: volume, energy, internal energy, enthalpy, and entropy. But notice they're exactly the same here. We just have the word specific tagged on the front of those 5 properties. The symbols for them are the same, except now notice they're all lowercase letters. So that's the significance of lowercase letters in this course, for these properties at least, is that those are the specific versions of each of those properties. So we now talk about specific volume, specific internal energy, specific enthalpy, specific entropy, etc. Now, what's the difference between the two? Well, the answer to that is in the units. Notice that these units are all the same, except they're now on a per unit mass basis. So volume divided by mass is specific volume. Energy divided by the mass is the specific energy, etc. So the units are now meters cubed per kilogram, kilojoules per kilogram, etc. So the significance of the lowercase letter is that it's that property on a per unit mass basis. And in the name, that's reflected by saying specific volume, specific energy, etc. English engineering units, exactly the same pattern occurs. There's just an extra pound, and that's a pound mass, in the denominator of the units. So get used to that terminology. That specific refers to a per unit mass basis, and also that we use lowercase letters for the specific version of each property. So that's all of our properties on a per unit mass basis. Now sometimes we also look at these same 5 properties but on a molar basis. So notice in this list of property names there's just an extra word, molar, tagged on the front. So instead of volume, we're now talking about molar specific volume. And again, it's meters cubed because we're still talking about a volume, but instead of being on a per unit mass basis, it's now on a molar basis. So we're dividing there meters cubed divided by kilomoles, the number of kilomoles that there are. Now, in terms of the notation, we remind ourselves, or we denote, that we're talking about a molar version of this property by putting a bar over top. So there's still lowercase letters, but they have a bar over top. So the significance of a bar over any property in this course is that that property is given on a molar basis. And in English engineering units, we see the same thing. Only the mole now is a pound mole, not a kilomole. And that's the English engineering unit version of a mole. So molar specific values are on a molar basis, whereas specific values are on a mass basis. Next thing we want to look at is a process. We'll be talking about a lot of thermodynamic processes. And a process is simply a change from one state to another. Another thing we're going to be doing, especially early on in the course, is drawing a lot of property diagrams. And we want to show processes on property diagrams. So here's our first illustration of a property diagram. Now notice we don't have the vertical and horizontal axes labeled here, and that's just because that can be any two thermodynamic properties that might be convenient to show the process we're talking about. Early on in the course, a very common property diagram is going to be a PV diagram, where we plot the pressure of the substance as a function of its volume or specific volume. But there's lots of other possibilities that we'll see during the course for property diagrams. So a process is just a change from one state to another. So here we're going from state 1, following a particular path, and getting to state 2. A cycle is a series of processes that return the system to its original state. So the little illustration we have here, again, I haven't labeled the axes because it could be anything. There are 3 processes here that form a cycle. So process 1 to 2, 2 to 3, and then finally 3 to 1. So the key thing about a cycle is it's a series of processes. It doesn't have to be 3. There could be 4, 5, 6. Doesn't matter how many processes there are. But the key thing is it returns back to where it started. So because of that, this second point is true. For a cycle, there is no net change in state. So for instance, if this vertical axis happens to be pressure, the pressure change from 1 to 2 is 0. From 2 to 3, the pressure drops. From 3 to 1, the pressure increases. If we add up all those pressure changes, it has to come to 0 because we're returning back to the same state. So there's no net change in state for a complete cycle. And that becomes a very important characteristic of cycles that we can use to analyze these systems. Now, if you remember the introduction we did where we looked at 3 different thermodynamic cycles. Remember, we called those cycles the power generation or the Rankine cycle, the refrigeration cycle. Those were called cycles because the working substance is going through a cycle. It's going through a series of processes. Each of those were 4 processes that return it back to its original state. So remember, in the Rankine cycle and the refrigeration cycle, they were connected. It was a closed loop. So the working substance in those cases is going through 4 processes that return it back to its original state. So we're going to be drawing these types of diagrams for those cycles a lot later on in the course. The next thing I want to define is energy. So total energy, to be more specific, is the sum of 3 contributions: internal energy, kinetic energy, and potential energy. So when we talk about total energy in this course, it's the sum of those 3 contributions. So we want to look at each of those contributions separately next. So first of all, internal energy. So this is energy associated with the molecular state of the system. So if we look at any working substance and we look at what's actually happening to the molecules, internal energy is energy stored in some way by those molecules themselves. So the little illustration that we're going to use here, we'll use a diatomic molecule. So if we're talking about air as our working substance, air is made up of nitrogen and oxygen. Both nitrogen and oxygen are diatomic molecules. So N2 and O2. So it means that there are 2 atoms, nitrogen or oxygen, joined together by a bond. So this is just a little simple illustration of what a diatomic molecule might be modeled as. So an atom here and an atom here joined together by a bond. So if we add energy to a substance that is made up of diatomic molecules, it's got a few different ways that it can store that energy internally. One of those is by vibration. So these two molecules might be vibrating, in other words, moving closer together and farther apart at some particular frequency, and they store energy by doing that. The larger the amplitude of those vibrations, the more energy they're storing internally. So if we're adding heat or work to this substance, that's one of the things it can do with that heat or work, is just vibrate with a larger amplitude, store that energy internally in the substance by vibrating. Another thing it could possibly do is rotating. So you can think of this as a little flywheel spinning around. So as we add energy, it could rotate faster and faster to store that energy in millions and billions of little flywheels, essentially, in the substance. So this is internal energy because it's storing it internally in the substance. Another thing it can certainly do is translate. These are tiny little masses that are flying around, bouncing off the table, bouncing off your forehead all the time. So they possess kinetic energy. And it turns out, in fact, this is one of the most important of these forms of internal energy, is its translation, just the kinetic energy. So these are three ways that a simple substance can store energy internally. And more complicated substances like water, or perhaps a hydrocarbon, a longer chain hydrocarbon, stores energy in these same three ways. There might be a lot more modes of vibration that are possible in those more complicated substances, but as we add energy to a substance, it stores energy in these different ways. Now that shows up as an increase in temperature. We're going to talk about temperature later on, but the way that it's storing the energy is by some combination of these three forms. Kinetic energy is motion. Kinetic energy is energy associated with motion other than random molecular motion. So this translation that we were talking about here is technically also kinetic energy, but there we're talking about the individual kinetic energy of each molecule in the system. And they're, of course, randomly moving all over the place. The kinetic energy that we're talking about here is when the system as a whole is moving. So I want to look at a couple of different ways. If we have a little closed system like this, so a little container full of a substance that we're studying, and we take that entire system and chuck it across the room, in other words, give it some kinetic energy. That's the kinetic energy we're talking about here. It's true that all of these molecules inside of here might be bouncing around, but that's accounted for by internal energy. If we take the entire system as a whole and give it some velocity, we're increasing that system's kinetic energy. In the context of an open system, an example of kinetic energy might be this. We might have a container full of a compressed gas. We put a hole in this container, and of course that compressed gas is going to go whooshing out of that hole with some velocity. So if this is our system boundary that we're analyzing, then the substance has perhaps some appreciable kinetic energy as it leaves our system. And that is associated with not random molecular motion, but organized motion. All of the gas heading in the same direction with some velocity. So that's an example of an exit to our control volume where the kinetic energy might be important. So this is a closed system example of kinetic energy where the entire system is given some velocity. And this is an example of open system kinetic energy where, in this case, an exit to our control volume has some appreciable velocity. The last form of energy, or the last contribution to total energy, is potential energy. So this is energy associated with movements in a gravitational field. So here I've shown the direction of gravity just by showing the acceleration due to gravity as a vector down on this picture. If I take a closed system, which is just a container full of a working substance of some kind, and I lift it up in a gravitational field, I'm increasing its potential energy. A open system version of a similar thing is if I have a pipe and I'm pumping some fluid or a gas in the bottom of the pipe, and then it's coming out at the top here. So this is my system boundary when I'm analyzing this. The potential energy of that working substance between this inlet and that exit is changing, and that would have to be taken into account in the energy balance. So the potential energy of the substance is changing from the inlet to the exit. So that would be an example in an open system context of where potential energy change might be important. Next thing I want to talk about in this list of definitions is the idea of thermal equilibrium. So if a system is in thermal contact with the surroundings and no heat flows, it is in thermal equilibrium. Well, what do we mean by thermal contact? Well, this just means that it's in contact and heat is allowed to flow. In other words, it's not insulated. So this brings us to the idea of temperature. Temperature is the property that defines the state of systems in thermal equilibrium. And it's actually proportional to the average kinetic energy of the random molecular motion. So that random molecular motion that we talked about when we were talking about internal energy is proportional. The kinetic energy of that random molecular motion is proportional to temperature. So you can think of temperature really as a direct measure of the kinetic energy of the molecules as they're randomly moving around and bouncing off the walls of the container and bouncing off each other. So temperature scales. We talked about units already, but I just want to revisit this because there's a couple of other temperature scales that we haven't talked about. In SI units, there's degrees Kelvin, which of course is an absolute temperature scale, but a more common temperature scale is degrees Celsius. And the conversion between the two, if we want to be very, very accurate, then degrees K, Kelvin, is degrees C plus 273.15. But for our purposes and most engineering calculations, we just simply add 273. So degrees Kelvin is degrees C plus 273. In English engineering units, there are also two temperature scales. Rankine, which we've already introduced, is an absolute temperature scale, and degrees Fahrenheit is a more common, popular, everyday temperature scale. And again, there's a conversion between those. So degrees Rankine is degrees Fahrenheit plus 459.67, but again, for our purposes, the conversion that we'll use is just 460. So degrees Fahrenheit plus 460 is degrees Rankine.